Thanks for the opportunity to speak to you this morning. I'm not a small ruminant scientist. I'm actually a plant physiologist that works on rangelands and mostly cattle grazing areas, but I think a lot of what I say will have a bearing and an interest to your research area as well. And as Greg said, I'm going to talk about climate change and the implications for grazing lands. And I think a good place to start is just with the Earth's energy balance. We know quite a bit about it. We've known these things actually for more than 100 years, well over 100 years. We know that the radiation that comes from the sun that reaches the Earth's atmosphere, about half of it gets reflected over there on the left, goes back into space. But about half of that radiation is absorbed by the Earth's surface, and it tends to warm up, and then the Earth re-radiates back into the atmosphere. And it's here that we're interested in what's happening in regards to greenhouse gases. Gases like water vapor, CO2, nitrous oxide reside in the atmosphere. And they absorb that radiation and they re-radiate it back to the Earth. And they actually make life possible on this planet because they modulate the extremes of temperature that we would have otherwise. So that's sort of a quick lesson, 30-second lesson in greenhouse gases and why they're important. The concern is that those greenhouse gases are increasing dramatically. On the left-hand side are concentrations of greenhouse gases, CO2, methane, and nitrous oxide for the past 2,000 years. Actually, with ice cores and other measures, they're able to go back 800,000 years and further to look at what greenhouse gases were in the atmosphere that long ago. And for that period of time, they were fairly stable. It's not until the Industrial Revolution that you can see a dramatic uptick in concentrations of these three important greenhouse gases. On the right here shows the annual temperatures from 1880 until 2009, I think. And it shows compared to the average temperature across the Earth that these years were, for the 20th century, that these years were on average cold, and these ones were on average warmer than the average temperature. And you can see that the change in temperature over that 130-year period follows pretty closely the increases in CO2 concentration. So we know from in the last 100 years that temperatures across the planet have increased about 1.5 to 2 degrees Fahrenheit. What are the projections for the future? And these are projections from a number of global circulation models. They're what meteorologists use to project the future effects of climate change. And shown here are projections for the middle of the century and the latter part of the century, and what's called a high emissions scenario or a lower emissions scenario. So these models take a variety of inputs, and as you can imagine, they rely on things like human population growth, industrialization, things that are not known with certainty, but they have a certain amount of error associated with that information. So by running models where you consider, let's do a low emission scenario or a high emission scenario, you can kind of bracket the likelihood of future environments that we're facing. And the projections for the middle of the century are from 2 or 3 degrees Fahrenheit increase in the low emission scenario to something more in the neighborhood of 4 to 6 degrees Fahrenheit increase. And then by the end of the century, 5 to 10 degrees Fahrenheit increases in temperature. All of the models predict warming. All 21 models used in the Intergovernmental Panel on Climate Change predict warming. They vary in the amount of warming. And of course, the type of warming you get also depends on where you are in the country. Now, if the climate warms, all things else remaining equal, the atmosphere tends to hold more water. And meteorological models also can predict what the consequences of this are. And they are more precipitation worldwide, more extreme weather events. You can see in these projections for North America that are done in the 4 seasons of the year, that projections, the blue areas indicate actually increases in annual precipitation. The brown areas indicate decreases in precipitation. Looking at this type of a map, I guess what would concern me the most in terms of rangelands are these fairly consistent drying trends that we see in the southwest and southern latitudes. Here across most of the continental United States during the summer, but certainly throughout the year you find a pronounced drying trend in the southwestern portions of North America. This is something that's predicted very consistently by all the models. Another sort of hot region of the planet is the Mediterranean. That's another area that's sort of a hot spot where all the models seem to agree that this is going to be an area where droughts in the future are going to be more common. So of course, for grazing lands, that's a real concern. On the other hand, my projections would be that actually some of this increased precipitation in some of these regions, some of it could be flooding, but some of it could actually be good and could result in increased production in those regions. Now, by itself, warmer temperatures can have a number of effects on rangelands. Certainly, the longer growing season, we're already seeing that. Changes in plant development, some pests and diseases that maybe are adapted to warmer temperatures are going to become more prevalent. I've already spoken a little bit about the altered hydrological cycle. The projections are for more intense rainfall events. The timing of precipitation patterns is expected to change differently in different regions of our country and different regions of the world. Some regions are expected to have more rainfall again, some more drought. And the area that I'm interested in are plant species responses, and it turns out, and this is probably not very surprising to anybody who's gardened or farmed, is that plants are quite variable in their responses to temperature. So some are going to be favored by warmer temperatures, some are going to be disfavored, or they're going to be outcompeted, or different types of crops are going to be sown in areas where previously they were too cold to sow them in those particular regions. Now, if we just think in a general sense about the effects of temperature on plants and consider that temperature stimulates enzymes and reaction rates and the physiology of plants, but it also affects evaporation, so it can actually result in desiccation. You can consider that increases in temperature by themselves can have both positive or negative effects. The positive effects are the longer growing seasons, increased plant growth rates. It stimulates the cycling of nutrients in the soil, so that can make nutrients more available to plants, and this can actually enhance their growth. These types of positive responses are expected to be most important in areas that are humid to subhumid and where the climate is temperate to boreal. But warming can also have negative effects. It can cause desiccation, which can actually shorten the growing season when you run out of water earlier in the summer. And it can also independently affect plant phenology, so the plants just stop growing because they've accumulated enough growth units. So it can actually have both positive and negative effects on plants, and the particular outcome depends in large part where you are in the country. Because you have these compensating effects, positive and negative, it's also true that often when people do warming experiments, they find that in the end, some of the positive effects offset the negative ones, so you don't really get any change in plant production. We know plants also respond directly to carbon dioxide, and this is where a lot of our research has been spent over the last 15 years. CO2 is a substrate for photosynthesis, so all things else being equal, if you increase CO2 concentration, you increase photosynthesis, you potentially increase plant growth. We also know that just like temperature, there are different species responses. There are different functional plant types. Some respond more strongly. What we call C3 plants that have a metabolism that's CO2 limited under present day conditions, they tend to respond more to CO2 than warm season C4 grasses. Originally, we thought that because C3 grasses were more sensitive to CO2, that they might be winners in a future CO2-enriched world, and the C4 plants, which are mostly warm season grasses, would be losers. But we also know that CO2 closes the pores or the stomates of plant leaves. And it turns out that this response is really important, and I don't think even yet today it's emphasized enough, because it actually has a very important effect on plant-water relations. It makes the plants more water use efficient, so that's a good thing. And actually, because of that, I think some of the potential negatives of climate change are going to be ameliorated a little bit. They're going to be softened by this positive effect of CO2 on plant water use efficiency. Now, a lot of the information that went into learning about this came from growth chamber and greenhouse work. We know plants don't always grow the same indoors as they do outdoors. So in the last 15 years, there have been a number of experiments in this country and around the world using different types of instrumentation and setups where people put out chambers and so forth and increase the CO2 concentration to see really what effect it would have on the plant community. And an experiment we've got going on right now, we do this, we inject CO2 from these black plastic tubes that are positioned right at the top of the grass canopy just outside of Cheyenne, not far from here. And then we have these heaters where we can simulate the warming that we think is going to happen in the next 60 or 70 years. So this is a type of research that's going in to try to understand how plants are responding to CO2 and climate change. And as with the temperature responses, the responses to CO2 are all over the place as well. For instance, California annual grasslands don't seem to be very responsive to CO2. It's kind of a curiosity. Here in Colorado and also up in Wyoming, we find that we get a huge increase in plant production when you increase the CO2 concentration from what it is today, about 390 parts per million now. It was 330 parts per million when I was in graduate school, by the way. I told you how old I am, if you know how fast it's increasing. But anyway, Colorado shortgrass steppe and the Wyoming mixed grass prairie respond like gangbusters to CO2. Kansas prairie responds to CO2, but only in dry years. And this gets back to the water relations effect. It's these semi-arid grasslands that are really responsive to CO2. When you get into wetter ecosystems like humid prairies and you get into forested systems, they don't tend to respond as much to CO2. Just some examples, but the point being that for the most part, CO2 either increases production or it has little effect on plant growth. So it's kind of a positive counter to some of the potential negative effects of warmer temperatures. One of the areas that we're kind of interested in is looking back in time over the last couple hundred years of what's happened and trying to understand is climate change a part of that. And a good example is what's happened in the southwest U.S. This is a picture near the Jornada, near Las Cruces, New Mexico. And today it's mostly mesquite, creosote. It used to be a warm season grassland a couple hundred years ago. And the thought was that overgrazing and the removal of fire from these ecosystems, which tends to take out the shrubs, is responsible for its transition from a grassland to a shrubland now. But it turns out that mesquite responds really strongly to CO2. And warm season grasses that it's displaced do not respond so much to CO2. I still think grazing and the removal of fire is probably the main factor, but I have a hunch that CO2 has been important in the ability of these plants to move in and to become dominant in this ecosystem. We're seeing the same thing actually happening in the Great Plains further north. Today we're seeing these woody tree islands, honey locusts, different pine species that are becoming more prominent. And again, I think fire removal and in some cases past grazing was an issue. But I think these species also tend to respond to CO2, especially the woody shrubs. And so likely climate change and CO2 are involved in some of these transitions, but likely they're not the only thing. But it's important, I think, if we're going to hope to manage these lands, to begin to appreciate that management is the most important thing that you can do to have an ecosystem respond the way you want it to or you desire it to. But the climate change is probably a factor as well. And it's important to know if climate change is causing vegetation change to get a handle on what direction it's kind of pushing things. What about weeds? We know in general that weeds thrive in disturbed environments, and there's evidence that some, not all, but some weeds respond favorably to future conditions. This is one weed in particular, toad flax. This is in our CO2 and warming experiment. Without going into a lot of details, this represents increases in shoots, seed pods, and biomass. This is plants exposed to high CO2. This is plants exposed to high CO2 and warming. And these are plants under present ambient conditions. And I think it's pretty clear you can see that Dalmatian toad flax really likes these future conditions. So what are some livestock issues and options? You know, we could spend days discussing this, and I won't, obviously. But I think the important thing. Oh, okay. Sorry, I wonder what that was. The important thing is that keep in mind that how climate change is going to unfold and how it's going to affect livestock operations depends on where you are. For instance, in the northern U.S., because CO2 is going up, because they're going to get higher precipitation, because forage production has probably already been increasing somewhat its potential anyway because of climate change, and because the winters are going to be milder, it probably will have, at least in the foreseeable future, a positive effect on livestock production. I don't think that's the case in the Southwest. Remember, I pointed out in some slides previous that it's one of the hot spots where warming is going to be really important. And so producers are going to have to think about things like more water and shade, better adapted breeds, better species, maybe goats, where you have shrub plants moving into grasslands. I think the Southwest is really going to be one of the areas where we're really challenged with climate change in the future. But it depends on where you're at. Where I live here in Colorado, I think it's a mixed bag, but I think for the most part it's not going to be a big issue for at least 50 to 60 years. If things really get toasty and warm up really quickly, and there's uncertainty about how fast it's going to develop, although data I've seen recently suggests that CO2 is increasing faster than people had thought just a couple of years ago in the atmosphere. If things get really toasty, then places like southern Colorado, maybe where we're at right here, forage production may be at risk 50 years from now. I'll just say a couple things about forage availability and quality. Of course, it's when the forage is available and the quality of that forage that's important for grazing animals. I've already talked a little bit about climate change is going to affect seasonality of production, species shifts, temperature, CO2. Haven't talked about precipitation, but all of those can cause changes in species. I also haven't talked about nutrient cycling, but there's a fair amount of research that suggests climate has important effects on the cycling and availability of nutrients for plants. Sometimes those changes may be negative, sometimes not. We don't really know yet. Certainly changes in species composition have a profound effect on grazers. And we think that those changes are underway right now, and they're going to continue. So, very briefly, my conclusions are that climate change and CO2 have likely already affected rangelands around the world. We know that CO2, temperature, and precipitation can affect plant production. It can affect species shifts. But because plant communities are very complex ecosystems and they have different climates depending on where you're at, they have different plant communities and soils, and you have different management practices, projecting exactly how species are going to shift climate change is, I think, a very difficult thing to do. We know it's happening, we can see the evidence in our experiments, but projecting exactly what's going to happen in the future is still, I think, fairly difficult. But because it's happening, and because we have reason to believe that it's going to continue and maybe accelerate, I think rangeland monitoring is really important. It's going to be even more important in the future if we move into this uncertain period where actually it's always been uncertain, but I think it's going to become a little bit more uncertain as weather patterns become a little bit more variable. One conclusion I've come to in the last couple of years from reading the literature is that I think southern latitude rangelands, and especially the Southwest, may be particularly vulnerable because of the droughts that are projected for that reason. But regardless, whether you're in the Southwest, northern Great Plains, the Pacific Northwest, weather patterns are expected to become more variable, and that variability, I think, is going to be an important factor for livestock managers to deal with their operations in the future, and I think that's just the road that we're on, and we're going to have to learn how to adapt.